Hi, this is Sri Ranjani. Today we are going to see how the reference signal is generated for inverter three-phase inverter circuit or three-phase shunt active filter or solar powered integrated inverter or battery connected inverter. So in all the three-phase inverter circuit, we will find out the reference signal. We will generate the reference signal from the supply current or load current with voltage as the reference signal. So here I have taken a three-phase load such as 230 volt 50 hertz three-phase supply which is connected to a three-phase diode bridge rectifier and then DC load of resistance 20 ohm. So this three-phase supply R phase I have taken as 230 volt into root 2 because we have to give the peak amplitude. So the single phase voltage is 230 volt RMS. So peak amplitude is 230 into root 2 and frequency is 50 hertz. Then Y phase amplitude is same voltage but the phase degree is minus 120 degree and B phase is minus 240 degree. Then this three-phase supply is connected to a voltage measurement block. Here I am using 2019 MATLAB version. So here the label I have enabled this use a label. Then label name I have taken as VABC and the current as IABC. Then this three-phase voltage current measurement is connected to the three-phase diode bridge rectifier. Universal bridge is taken and I have selected the power electronic devices diodes, and even if you want to use thyristor you can use it, and pulse generator you can connect it. And remaining all the values I have taken the default value. Then the DC side I have connected resistance of 20 ohm pure resistance using the series RLC branch. I have selected only R with the resistance of 20 ohm. Then this voltage current measurement I have taken the signal label as VABC and IABC. So I have used the from block where I am measuring the RMS value of the voltage and the RMS value of the current which is connected to the display, and this is the mux I have connected. Then the RMS I have taken the fundamental frequency. Here I have enabled the true RMS value because this is the nonlinear load. So our fundamental RMS value and the true RMS value is different. So we will see what is the difference now. Then later I have connected the power block where the voltage and current. Here I am measuring the single phase power only. So I have used the Dmux here and then voltage and current. Then that from that I have taken the only single phase R phase voltage and current to the power block, where the power block fundamental frequency I have taken as a 50 Hz. Remaining all the value it is same. Then it is connected to the mux block that will show you the active power and then reactive power. Then we are generating the reference signal with the fundamental frequency component. So fundamental frequency component, whatever the magnitude, that magnitude we will see it here. So in order to verify whether we are getting the same magnitude, I have connected that IABC signal to the Fourier block where the fundamental frequency 50 Hertz. I am going to take the fundamental frequency component only. So here I have taken the harmonic n value is 1 because 50 Hertz frequency whatever the magnitude I want, and I am going to connect it with the display. Then this magnitude we can convert it into the RMS value, fundamental RMS value. Whatever the RMS value we are getting here, that will be different from this RMS value because Here it is a nonlinear load, so it contains the harmonic component as well as the fundamental component. So this RMS value will give you the fundamental component plus harmonic component, and this value will give only the fundamental component. So the RMS value of the fundamental component we will get it here. So simply I have taken 1 by root 2 because Vrms is equal to Vm by root 2. So this gives you Vm, so Vm divided by root 2, that gives the RMS value. Then coming to the reference signal generation. So what I have applied is the algorithm is synchronous reference frame. So here the current signal. So current signal IABC and VABC as the feedback signal. So this signal is given to the alpha beta gamma block. So what is that alpha beta gamma block? Here we are connecting this as this is the expression to get the alpha beta gamma, and alpha beta is again converted into DQ. So this is the formula we are using to convert that ABC to DQ transformation. First we are going to convert ABC to alpha beta transformation, then we are going to convert into DQ. So this equation we have represented in terms of gain block. So first 2 by 3, that is multiplied by this. Inside this bracket we are giving the first row with the space, and then second row and first row was given in terms of semicolon. Then again second row we have taken with the space, then semicolon, then third row we have entered. So here the multiplication we are not going to, normally in default it will be in the element wise it will be present. We have to take it as a matrix K star U vector, that we have to select it so that it will perform. Then in order to get that cos theta and sin theta, here cos theta, theta is omega t, where omega is 2 pi f and t is the time period. So here we are going to use the 3-phase PLL circuit. For that we have to give the reference voltage VABC, and we are going to take it omega t. So here that frequency alone I have changed, remaining all the value I have not changed, it is a default value only. So omega t we are going to give the sine block, that is the trigonometric function block, and then cos function block. I have not changed anything, only the function I have taken sine and then cos term. So that is given to this mux block. Then this mux block is given to the DQ transformation, where we have to get the ID as cos theta I alpha plus sin theta I beta. So this is the expression given in the function block u of 5 star u of 1, because this contains the alpha beta gamma, that is 3 output, and u of 1 to u of 3 that will be coming from this gain block, and u of 4 we will get it as a sin omega t term, and u of 5 we will get it the cos omega t term. So the first one is cos omega t into I alpha. So this is the equation we have to write it. Similar way we are going to get that IQ as minus sin theta into I alpha plus cos theta into I beta. So this is the equation we have to write it for this IQ. Then we have to mux it, and we are getting the mean value DQ, because we can use the low pass filter or mean block to get the average value. So that after getting this DQ, again we have to convert, because a reference signal we have to generate. So DQ to alpha beta to ABC. So the input for this block is the reference signal V, that is the voltage signal given to the same PLL circuit in order to get sin omega t and cos omega t, and whatever output we are getting from the block is given to this second block, which will generate the sine wave. So the DQ is coming here, so DQ is given to this mux, and VABC same PLL we are taking here, and then this is given to sin omega t cos omega t. So first it will perform this function, that is we have to connect a function block here, u of 4 into u of 1 minus u of 2 into u of 3. So this function is performed here. Again in this block u of 3 into u of 1 plus u of 2 into u of 4, because DQ there is 2 output is coming, and here it is the single output we are getting. then that is given to this gain block, where gain block, same thing we are going to use it. That is first row we are writing here, and semicolon second row, then semicolon third row, which is again we are going to use the matrix K into U. So that is given as the ABC sine wave, and sometimes we will use the harmonic current as the reference signal. So we can convert that actual current minus fundamental current, that will give you the harmonic current. So both current we are getting from this reference signal. So while we are running this simulation, we will get the signal, that is the actual current. So if you see here, here we are getting the supply current here. Then from the supply current you are generating the reference signal, and harmonic current also we can take it as a reference signal. So the fundamental current, it is fundamental current we are generating as a reference signal, or sometimes we will use the harmonic current as the reference current, so that also we can use it. Then coming to this signal, here this is the nonlinear load we are taking. So here the current, if you see that the current is 21.99, that is 22 amps is the current, fundamental current. And if you see the this is the true RMS value, then if you see the fundamental current is 21.02, our reference current signal generation also creating the RMS value was 21.02. So here this is the true RMS and this is the fundamental current. So here even we can find out the FFT analysis by keeping that the signal here in the scope. We can get the settings and logging, we can get the scope data 3 structured with the time, so that we will get the signal here. So in this we are getting the workspace out, we are getting the scope 3 data. So scope 3 data we can take it as A1 is equal to out dot scope data 3 semicolon, so that we will get the A1 as the structure. Now if you see the FFT analysis here, so you go to the discrete time, I have taken 5 e power minus 6, and tools, you go to that tools, FFT analysis. So here A1 is coming, here the input current is your lower line current, that is the supply current here. Then you can do the display. So see here your fundamental is 21.02, same thing we are getting 21.02, and your magnitude is 29.72, same thing in FFT analysis as well as here we are getting in that Fourier transform. So both here the reference signal we are getting the same value. Here if you see this FFT analysis, the fundamental phase angle is 0. So fundamental angle is 0, only the reactive current is due to the harmonic current. Suppose you are connecting the reactive load, whether the same reference signal can be used for the reactive load also. We will verify that also. That is, one inductive load we are connecting with the resistance R 8 ohm and inductance 20 into e power minus 3. We have not changed any that is in control algorithm, we have not changed anything, just we are keeping the same reference signal circuit, and we are going to verify that whether the reference signal is same or not. The RMS value is whether it will generate the fundamental current alone or not. So when we are adding the inductive load, in that case whether SRF theorem can be applied for the reactive load. So now if you see here, the frequency, that the phase angle is minus 19.87, and if you see the RMS value of the reference signal generation is 50.62, but our fundamental component is only 41.23. Okay, so what is happening here? Whether this algorithm is not suitable for reactive load, reactive power load, maybe. So how we will find out that? Okay, so this is the signal we are getting. This is the supply current, where the supply current is not in phase with the supply voltage, so there is a phase lag, that is the 19.71, that is the lag degree, where the voltage and phase angle between the voltage and current. So if you apply the synchronous reference frame, so what is happening to the fundamental reference current? See here, whatever the phase shift it is occurs in the supply current, same phase shift you are getting in the reference current also. So synchronous reference frame, we are not able to use it in the reactive current load as it is. So we can modify that algorithm so that we will get the reference signal as pure sinusoidal, also in phase with the voltage, supply voltage. So in next video we will see how we can modify the algorithm so that we will get the RMS value as same whatever we are getting in the FFT fundamental current, whatever that RMS value, same RMS value, whether we can able to get it or not. In the next video we will see you.